So topologic, what is topologic? Whenever I talk about topologic, there I have two goals. First is to explain what it is, what it does. And then once you understood that, to explain why it matters. Because people say, okay, that's great, but how can I use it in my workflows? So I'm going to start by looking at this animation, this turntable animation that's going around. It is obviously, it looks like an L-shaped building of some sort. It's an abstracted form of it, so it's much simplified. There is a kind of a central atrium, perhaps in the corner, you know, this red tower, and then some vertical and horizontal circulation, maybe those green pieces that you see here. And then there are spaces around, but you'll notice something different about this, this model. First of all, it is, as I said, very abstracted. Everything is made out of zero thickness surfaces. It's translucent. And inside of it, there is this kind of like strange mesh, right? There's this strange wire made out of vertices and edges. Those vertices and edges make what we call a dual graph, basically a network of lines. And the nice thing about this dual graph is that it is a different representation of the building, where a vertex can represent perhaps a room or a surface or a door, and then the line, the edge, represents some kind of topological connection, some kind of adjacency, saying this room and this room A and room B share a surface. And when they share a surface, or what we call a face, we draw a line between those two rooms. So that's what you are seeing kind of hidden in the middle of it. But there is something else about this model. It is also color-coded. So what do these colors mean? You'll notice that the atrium, this tower, is red, is bright red, is hot. And then the ones at the very end are very cool blue colors. Why is that? What I have done here using Topologic is I have measured the distance from each room, each space, to every other room and averaged it out. So basically, you get a score for how close is this room to all the other rooms. So what that gives you is that central rooms, things that are close to every other room, get a higher score, and things that are isolated get a lower score. So very quickly, through color coding, you can analyze your building and say, do I have some offices that are really isolated? Should I change the design to integrate them a little bit better? Or this space is really central, so maybe that's a really good place to put the entrance to the building or to put the coffee machine, in order for people to because they will be passing through it a lot, because it's a central space. So it's a measure of centrality. If you know about an area of research called space syntax, they do a lot of that as well. So it's a very similar to space syntax type of metrics. This is recent. This is actually from yesterday. This is also on osart.org. So this is Bruno Bretaccio, who is starting to learn Topologic. And he created this very simple model here, where he has this 9 square, 3x3 squares, and he has these cubes in there that have a title. They're called living room, they're called bedroom, they're called bathroom. And he's moving these spaces around, these little cubes around. And when he does that, Topologic can find out that these things exist in a certain room, and then says, okay, so now I recognize that I am a living room. And because I am a living room, I probably need windows. So he has decided on a rule that living rooms should have a lot of glazing. So it looks at, so which walls are the exterior walls, and therefore I'm going to turn those into glass. So you see them turning from green solid into a blue glass window, glass wall. And therefore, you know, with Topologic, you can play this kind of what-if analysis on your building before complexity sets in. This is all done in the early stages of design, where you're trying to kind of come up with a strategy about what you want to do and looking at how you can organize your building. So going back to the team, I just need to acknowledge that obviously this is not a single person's effort. This was a team that we were funded by the Leverhulme Trust. As Nancy said, I collaborated with Professor Robert Aish, and Dr. Simon Lennon, and Dr. Katerina Khatsiba-Zilyadi, and Dr. Nicholas Wardhana. We formed a team. We were funded for whatever, 300,000 over 3 years. We were really lucky and privileged to be able to spend 3 years developing this software. So why do we call it topologic? What is this idea of topologic? So we were trying to come up with a nice name. Actually, the name is Robert's invention, which is really nice. But we noticed that when we're dealing with BIM models or with architectural models in general, with 3D models, we can have we can have the geometry, which is how the thing looks like, but then there is something about how it is connected. So things can change shape, but continue to be connected the same way. The classic example is that a torus and a coffee mug are both the same thing because, it's a connected thing with a hole in the middle. So if you look at this model, this is something from the internet called the tesseract, you'll notice that it is drastically changing its shape, right? Sometimes it looks like a cube, sometimes it's more trapezoidal or a diamond shape, but the topology, how the vertices are connected to each other, remain the same. They never change. The same vertices remain connected to the same other vertices. And that's what we are interested in, is to see how geometry and topology kind of interact in architecture. So here we get into a little bit of a esoteric term, but don't worry about it. It's just part of math. But what is this thing we're saying? We are dealing, topologic deals with something called non-manifold topology or non-manifold geometry. What is that? Let me explain it in very, very simple terms. Most of the CAD systems that you have, create solids, let's say a cube or anything like that. So think about a cube in your hand, like a 3D cube. Every point on the surface of this cube is separating its own world into two sets. There is the outside world, everything outside that cube, and then there is the solid material inside that cube. So if we call the outside set a manifold, and the one inside also is another manifold, you get two manifolds. So two manifolds, for short, we call that manifold. We just don't say two manifold, we say manifold. Now, so what is non-manifold? Non-manifold is when a point on the surface connects or sits in between more than two worlds. It sits between 3 worlds or 4 worlds or 10 worlds or 1,000 worlds. So if you look at, for example, in the sketch on the right, and you look at the red dot, at the very red dot, which is the intersection of 3 cubes, you can say that this red dot is sitting between at least 3 or 4 manifolds, right? There are 3 cubes around it. You can jump from that point to the inside of these cubes, and then there is the outside world. So that is a 4-manifold world or 4-manifold condition, and we call that non-manifold for short. Instead of saying 3 or 4 manifold, we say it is non-manifold. Now, how does this relate to topologic? We like to take a building or a shape and then slice it with planes, internal planes, to create cells. So anything that is sliced on the inside and is cellular in nature is non-manifold. So we have to deal with it mathematically. But this is kind of like low-level math that we deal with behind the scenes. You don't really have to deal with it when you are using the actual software. So basically, at the bottom of our system is, of course, numbers and math and zeros and ones. On top of it, we have geometry. And on top of geometry, we have added a layer of topology to kind of describe how things are connected. But we didn't stop there. On top of that, we added information, or what we call semantics. So we can say, this is a living room, this is a kitchen, this is a window within a wall. So we can add information on top of topology. So what does topology and semantics, how do they affect our understanding of the world? If we are dealing only with geometry, I can very simply take a look at this diagram and say B on the left is closer to A than C is to A, right? We can take a ruler and measure it and say, yeah, B is closer to A, we can measure that. But if we talk about topology, we can say different things. For example, you'll notice that I have added these black circles. And you'll notice that there are more black circles between A and B than there are between A and C. So topologically speaking, because there are more hops, we can say that actually B is further away from A than C is from A. Why is that? That is because topologically speaking, there are more stops on the way from A to B than from A to C. Now, that can make a lot of sense to you if you think about traveling, especially in the US, where there are a lot of hubs. and you're traveling by air and you need to have a stopover and a stopover and a stopover, we know that a direct flight, even if it maybe to a further away city, might actually get you there sooner than a close city that has multiple stops. Now, if we add information and say, this is not just a line, kind of abstract line, but it's actually roads, and the road from A to B is littered with construction, littered with a red light that takes forever to turn green, you'll notice that now topology as well as semantics, make sure that this, definition of A being closer to C than A to B holds true, because it all has to do with information. If A from A to C is a highway that you can go whatever 70 miles an hour, 100 miles an hour, you can obviously get to C faster than you can get to B. So the idea of adding topology and semantics really changes the game for architecture. The other thing that we our philosophy when we were designing topology is this statement, complexity last, not first. And the idea here is that when we are using BIM systems, we notice that it invites complexity at the outset. From the beginning, they're telling you, learn about foundations, learn about slabs, put your doors, figure out which manufacturer is gonna, what manufacturer you want for your doors and windows. And you're immediately creating the building fabric, even before you decided on the strategy and the overall shape of the building. It's asking you to put in a lot of complexity. With Topologic, we wanted you to postpone complexity to the very end and deal with the lightest possible model that you can create that has embedded in it the most amount of information, so that you can later on allow either software or other people to add that complexity. So you'll notice here from Vitruvius, he's describing this Corinthian column, and he does not describe all the leaves and all the sculpting that's going to happen, because that's going to happen at the very end. He's describing the basic parametric shape and how you are going to construct the basic capital, and then obviously complexity comes in later as added decoration on top of it. So we always say that for BIM, BIM, the way it's moving, software is going to be the main method by which BIM models are populated. It's not effective. It's really not a good use of our time to spend time, putting seats in a conference room and to put furniture in rooms and offices. Software can do it much better and much faster, so might as well do that. And then architects and designers can focus on the strategy, on setting out the strategy for the building. So Topologic deals with space. It abstracts things, as we've said. It kind of, deals with things at a simpler level, but it creates entities that are aware. They're aware of their place in the world. They know their neighbors. So if you ask yourself, think about your favorite 3D system, 3D Studio Max, Maya, Grasshopper, Rhino, whatever have you, and think about building like a tower, like a block of, some blocks on top of each other, and say to yourself, can I ask one of those blocks, which blocks is above you and which block is below you? And it will take you a long time to figure out some kind of Grasshopper definition or some method in order to answer that question. With Topologic, that answer and that question is built in. So anything you build, you can just simply point to it and ask it, so who's to your left, who's to your right? Do you share an edge with something? Do you share a space with something? And these types of topological relationships, I'm not going to spend a lot of time on these slides. I'll skip through them a little bit. They can be like sideways, and they can be hierarchical. So you can go from complex shapes to simple shapes, like you can see here, from a cell complex all the way down to a vertex or a set of points. You can also climb the tree, etc. So everything in Topologic, this is now your first image of Topologic working in Blender. It works in Blender, Grasshopper, and Dynamo, by the way. You can subdivide the your object into sub-objects, and those sub-objects into smaller sub-objects. So you can kind of unpack it. So yeah, this is the torus is what we started with, that gray torus in the middle, and it, we exploded it into these faces and we moved them over. So you deal with Topologic like this, you kind of drag and drop nodes and you connect them to each other, and that starts building the logic of your workflow. As I said, you can climb up, so you can ask a vertex what edge it belongs to. You can ask an edge what wire it belongs to. You can ask a vertex what cell it belongs to as well. So you can jump over multiple steps and go to the higher level kind of topologies. So there is also something called lateral topology, sideways. So basically in here, I have a building. I pick the corridor, which is highlighted in yellow. I exploded it so that you can see it. Then I ask this corridor, this big yellow corridor, give me all the spaces that are touching you, all the spaces that are adjacent to you. And it gives me all these red spaces, and I color code them in red. And obviously it's most of the spaces on that floor. It also has kind of topology or connectivity at a distance, basically the shortest distance. So basically in this example that you see here, I'm trying to get from the green button, from the green cube to the red cube, or vice versa. But I also want to avoid the spaces that are crowded. There's COVID in the world, so I want to go, through empty spaces. So as you put these particles, as you can see here, these dots in spaces, it will find the shortest path that avoids those spaces, because it is not just topology, it's not just the shortest path, it's also with the added semantics, with the added information. So it asks every room, how many people are in that room, and if there are a lot of people, it says, no, that gets a low score from me, so I find a different path. Imagine using Google Maps, it's the same thing, right? Do you want to get there through roads that are not very congested, or through country roads rather than highways, etc. Right. So, and we can have apertures, we can have windows. So in this case, we are able to say, well, this is a wall, so you cannot go through it. The yellows are windows or doors, so you can get through them. And we have, as we said before, this is another example of that building that I showed you that was rotating, in the sense that we implement what is called graph theory fully. So you can find things like the shortest path, you can find centrality. So you'll notice that the head of this grasshopper is the lightest green, perhaps, is the most central space, and all the extremities are obviously isolated, and they're far away from everything else. So that's the color coding that you can do in there. This is called the minimal spanning tree. Basically, given a very complex shape, very complex graph, what is the minimum set of lines that connects every point to every other point? And that could be a really interesting place to put all your circulation, for example, because it's guaranteed that this yellow minimal path will connect all the points to each other, and the other ones are simply extra. They are not needed for circulation. And you can do graphs on spaces, on 3D spaces, on shapes, on lines. Anything can have a graph, really. Basically, a cell will have a single vertex. A face can have a single vertex. So what you're seeing here is a shape, and then the lines and the yellow little squares are the duality of it, the dual graph of it. Same thing here, just connecting different options to connect to exterior topologies or exterior apertures. And then semantics. So here's what's so interesting about Topologic. Semantics, or we call them dictionaries, basically are affected by and affect the geometric operation. What do I mean by this? Let's assume you have a living room and a kitchen in your space, and you intersect them somehow, 3D intersection, some kind of operation. The space that is intersected will inherit the dictionaries of the two parents. So that dictionary will say, oh, I am the child of a living room and a kitchen. Well, as you write your software, you look at that and say, okay, anything that is the child of a living room and a kitchen, make that into an informal breakfast area. And therefore that kind of power of saying, I know where I came from, allows you to make decisions down the line about what you want to do with your architecture. If I have, for example, a wall that says, I'm a wall that separates a waiting room in a hospital from the X-ray room, where the X-ray machine is. You can make a decision, this wall will know that, and you can make a decision that it should be lined with lead or something thicker so that radiation doesn't leak into the waiting room. Or, as you saw earlier, I am a living room and I have a wall that is separating it from the outside, and it's a living room, therefore let me make it out of glass so that I can enjoy the view. this type of semantics is embedded and can travel through geometric operations as you do them. It's always there inside the geometries, embedded right inside the geometries. So you can do things like pathfinding, you can climb up stairs, you can do multi-objective optimization. For example, you want to increase the glazing area, but also you want to be careful about cooling loads. All of that is available to you. You can connect it to energy analysis. You can connect it to fire analysis. In this case, we connected it to something called FDS. So you can do fire simulation or smoke simulation, and then find out the temperatures and do all sorts of analyses with it. Again, there are papers published on these things. If you would like more information, just take a look at our website and you can see these things. We've connected it to a branch of AI, of machine learning called reinforcement learning. And reinforcement learning is basically like training a pet or training an animal of some sort or training a robot of some sort. In this case, what we are saying is that this yellow cone needs to find those green spheres. And so we're saying maybe this is a fire egress, like a fire exit door, and it needs to find them. At the same time it's trying to find them, there is a fire kind of brewing in the building. And those are the red spheres. They're growing in temperature, right? Growing in smoke or whatever it is. So we're not saying that this is how people will find these exits. It's not a simulation of crowd behavior, but we're saying that this could be a method by which you can compare whether the placements of your fire egress makes sense or not. So if I put 3 or 2, it will probably have a harder time finding the 2 exits rather than 3 exits. Or if I put them very far away, it might be consumed by the fire before it gets to them. So you can use this as a surrogate model to analyze your building by using reinforcement learning. Reinforcement learning basically rewards the agent if it makes a good decision and punishes the agent if it makes a bad decision. And then you build this kind of quality tree. So we tried it on the Revit model, that sample model that comes with Revit. And we started the fire up on the 2nd floor, and we put a lot of these green exits, green balls, sort of like safe havens. And we want just almost like a game and saying, can you find them? So we put some on top to kind of like deceive it and say, would it go for the ones on the 2nd floor, which makes it go right through the fire, obviously, which is dangerous, or would it find the ones at the bottom? And lo and behold, obviously, as you can see the path, it ducks down immediately through the vertical circulation and tries to exit before the fire consumes the whole building. So we used it also. Topologic is now also embedded in something called SAM, which is used by a company in Bristol called Horlia. SAM is like a big glue software that connects BIM and analysis software like OpenStudio, etc. And they rely on Topologic to clean up the geometry and create an energy model. So you can take a look at that. So this is kind of a part of what they're doing. So you can see some topology nodes right here in the middle before creating what is called a GBXML file. Ahmed Tahlawi is a brilliant architect working in Germany. He and I have been collaborating on moving what is called test fit models. There's a company called testfit.io that creates these simple models really, really quickly to kind of test the feasibility of a project on a site. We have embedded that with information, and we have moved it both to Revit and now to Blender, and then we're soon going to move it to IFC files. So this is now working recently in Blender. I call that the anatomy of a building. So basically you can take a topologic cell complex and you can ask it for its exterior walls, you can ask it for its floors, you can ask it for interior partitions, you can ask it for vertices that have only 3 lines connected to them. So this is what you see here, is like, just give me the points that have 3 lines connected, or give me a point that have 4 lines connected to it. And you might want, that might be useful to you, and you might want to make some decisions based on that. It basically breaks down the object or the building into its components and in a very intelligent way. Miguel, is a good friend of mine, and he's using it at his PhD research, where he is kind of overlaying this with a lot of information about the spaces, and then he uses that with an interface to convert it into a BIM model. And you can change, again, if you change the information, the BIM model updates automatically. Everything gets resolved in terms of inside and outside. Bruno Postel created a piece of software on Blender called Homemaker. He and I, again, have become friends, and he's using Topologic inside his software. So the idea is that you create a very simple massing model, as you can see in the upper left corner. You slice it, and then he automatically recognizes this model and then converts it intelligently into. He likes neoclassical architecture kind of type of architecture for this, but you can really replace these windows with anything you want. They're all IFC objects, so you can replace them in any style you want, but he prefers this style. So the idea is that from this very simple conglomeration of buildings, as you see in the lower left corner, you can build something really, really complex, and you don't have to change. Move windows and change foundations, change walls on the complex model. You go back to the simple topologic model, change it there, and then rule-based systems will again populate the BIM model intelligently. We have also a few PhD students. I think some of them are here. This is actually, sorry, an MSc student, but he's been collaborating with a PhD student. So this is a recent dissertation at the master's level, where he combined the idea of doing graphs with graph learning. So there are neural networks, part of machine learning, that learn graphs. Facebook uses it to kind of predict, who you should be connected to, who you should learn about, or Amazon uses it to figure out, what's the product that you're going to buy based on what you have bought in previous times. So basically, it predicts, connectivity between graphs. And because a building for us is a graph, as I showed in the beginning, you can train it on types of buildings, and it can then generate new buildings that match what it has been trained on. I have worked also with my PhD student, Abdurrahman al-Yamani, who used, again, this idea of graph machine learning. It's part of his PhD, where we created, for an urban block here, we created the graph for it. So basically we have, one vertex for the ground, one vertex for the podium, a lot of vertices for the building, and we created thousands of these variations. And we use this data set to train a graph neural network. And then we give it a new one that it has not seen before and say, tell me what kind of building, what kind of urban block is it? It will say, oh, this is a tall building sitting on the ground, or this is 2 towers short sitting on a podium, whatever have you. It can recognize now kind of new building typologies. So maybe you can make a decision on that. So this is the latest image that he sent me. This is all synthetic data sets that he is creating in order to train this neural network. So that's it for me. That's Topologic. If you want more information, go to this website, topologic.app, and you can find out more about our software.
Wow, that was great. I'm sure that stimulated some questions. You ran through things very quickly, which I very much appreciate. There were some amazing things where you were generating these variations. Maybe you could just explain, while other people get their questions ready, if you can put your hands up, I'll see the hands hopefully, or you can write them in the chat. Just curious if you could explain a little bit more about the typological things that you showed in the last slide. I thought that was extremely powerful.
These ones?
Yeah.
Yeah, sure. So basically, as I said, there is a branch of machine learning that learns from graphs. So basically, you feed it a network. You feed it something that looks like the bottom images here. I don't know if you can see my cursor, but basically these graphs at the bottom, you can feed it that, and it will learn the relationships between them. So you label the vertices. So it will learn on those. And then when you give it a new graph, it will tell you overall what type of graph it is. Basically, you classify the graph. You say, this is a building, this is a mall, this is a hospital, this is a school, right? So as if you feed it more and more graphs that are of type school or of type hospital, then you feed it a new one, it will recognize it. It will tell you, yeah, that looks like the graph of a school, within a certain limit of accuracy, obviously. So, my PhD student, Abdurrahman, he wanted to figure out whether the computer can recognize the relationship between the building and the ground. So basically, if you can imagine, your design, it could be hovering over, or it could be embedded, or it could be sitting right onto the ground. There are all sorts of relationships that you can have between the building and its surroundings. So what we have decided to do is let's design a synthetic database, because it's really difficult to get it from BIM models and from magazines and stuff. It's really difficult because we needed thousands of them. So we created a parametric definition that creates these relationships and varies them in different ways, in a very abstract, simple way, obviously like a block world type of thing. So what you're seeing here is like 3-story building or a 1-story building. Sometimes it's embedded, sometimes it's 1 tower, 2 towers, all sorts of variations. We build a topologic model. We can recognize what is ground, what is a column, what is a building. So these are the color-coded graphs. And we take all that information, we make a graph out of it, and we feed all these graphs into the neural network. And then we give it new graphs that it has not seen before and ask it to identify them. I mean, obviously, we know what they are. We ask it to identify them. And we measure the accuracy. And of course, as with any machine learning approach, you have to kind of fine-tune the hyperparameters, how much you are going to allow it to learn, epochs, batching, all sorts of hyperparameters that you need to change in order to improve the accuracy. So we went, initially when we first tried it, maybe we had like 63% accuracy. We can go to 73%, 85% later on. So we can improve the accuracy of these machines.
That's really great. It's very interesting to see how you can categorize buildings according to their topology. I have a student here, Tanner, who's interested in how you would use this in different phases of design. I don't know if you have to talk real loud.
I was wondering, are the lightweight representations of physical models relating to structure and form best used for early concept work, or would you use this for more kind of final drawings and work?
Definitely early phases. But we had an image of sort of like topologic, on top, and then lines radiating into like a structural analysis model, energy analysis, daylight analysis, building fabric BIM model, all sorts of derivative models. So what we are advocating is that start with a topologic model, build this kind of lightweight model, keep it alive as long as you can, because it's lightweight, as you said, and we can change it very quickly and we can extract a lot of information before we commit ourselves to like exactly what type of external wall, what kind of building envelope, what kind of doors we want to put into it. And we can change our minds a lot easier, because if we have the rules that convert this abstract model or conceptual model into a BIM model, I can go back and change the conceptual model, and then it will simply trickle down and repopulate my BIM model. If I had to do it myself, I would be tempted not to change anything, right? Once you build a big complex Revit model, the last thing you want to do is change it, which goes against the original concept behind BIM. The whole idea behind BIM was that everything can be changed. We can iterate many, many times. So yes, we want this to become what we call a driver model, like a lightweight but kind of strategic model where a line can become a beam, a vertical line can become a column, a surface can become a wall, and we have you can make rules about how to change this conceptual model into a very complex BIM model, whether it's IFC or Revit or whatever have you.
That's great. We saw your example. Thank you very much. Thanks, Anna. We saw your example from Bruno Pro.
Yeah.
So, did you want to ask a question? So we have Max here, and then I'll go to after my students, I'll ask the audience. Okay.
Sure.
Yeah, I had a question about kind of the applicability of the model and the technology outside of architecture, because obviously it's really great for kind of planning the building in general, but since the model is so, it seems like it can be so ubiquitous that it could be used for maybe perhaps other fields as well. Do you anticipate any of that happening? Is that?
Can you give an example? You mean like landscape or something? Or?
Landscape, urban design, but even potentially other stuff. But I was focusing mostly on urban design, I think.
Right. I mean, obviously, it shares a lot with the philosophy of GIS systems. So in a way, we not borrow, but we have a lot of intersection with how GIS systems work, because they also work with a lot of topology, a lot of, but they are more about, really networks rather than, building three-dimensional, fully connected spaces. So they concentrate on that. So we see that kind of augmenting GIS systems. I have not yet encountered people who are using it in very different ways, but I know that there are a couple of companies that are using it for MAP, for HVAC and plumbing and all of that, because it's all network based. So you can imagine finding the shortest path for some kind of pipe through a building. So yes, anything that requires that, it can be helpful in that regard.
Great.
But I would love to hear about different possibilities for it. We do see it as foundational software. I mean, by itself, it does a lot, but it does not do a lot of domain-specific stuff. Like you need to build on top of it some kind of application that connects it to a domain, like to architecture in some way. But it gives you a really nice, solid foundation.
Thank you very much.
Thanks.
Okay. Hi, you have to get here so he can see you.
Hi.
Hi.
Yeah, can you hear me all right?
Yes, yes.
Yeah, so my question is, I was really just curious about what drove the initial need for this kind of like form-finding topological software. And I was really thinking, in what ways do you think the industry standards out there, such as like Revit and AutoCAD, are kind of lacking?
Sorry, just the last part, please. Can you repeat that?
Yeah, how do you think like industry standards out there are lacking? Like there must have been a need to make this. Yeah.
Yeah, I mean, this actually grew out of two things. I was trying to connect early design models with energy analysis. So I was doing that within 3D Studio Max, and I wanted to connect to Energy Plus and to Open Studio and try to take models and make them like energy models. And I was facing a lot of difficulty with that. So I went to a workshop in London at Autodesk, in which Robert H. at that time, he was with Autodesk, and he was talking about design script. He's the one in his team who invented design script, which is the language inside Dynamo. And then at the very end of the presentation, he talks about non-manifold topology and invites somebody from Bureau Happold to show a very, very quick demo about, oh, you can use this non-manifold building to connect to energy analysis, and kind of like lights went off, obviously. So I went and talked to him. So after he left Autodesk and went to UCL, we started talking a bit more, and we were honestly unhappy with the status of BIM in our community, because we found that BIM models are really hindering creativity. They're splitting us up into two camps. So we found people who are computational designers working with Rhino and Grasshopper and being very creative and creating these amazing models. And then we found another camp of people who spend their days fixing BIM models and dealing with the complexity of BIM models. So we found that it's splitting, and we wanted to bridge it. And what we found out is that it's very difficult to take these Rhino models and convert them to BIM models, because you have to redraw them perhaps sometimes. And then when you want to do energy analysis, it's very difficult to take BIM models and then simplify them back to make them available for energy analysis, because energy analysis just requires like simple cubes. It doesn't, all that walls and complexity it doesn't need. And that's what I was facing. So we said, can we take a look at that whole process and start it logically and say, can we create simple models, but are rigorous models, are really well-connected models, and models that can allow us to continue our journey forward.
Thank you.
Great,
Yeah.
That's great. We have one, you want to come up here, Alex? I'm going to stop the sharing of the screen.
Oh, yes.
I think it's great that you're doing these studies. Okay.
Hi
Yes,
there.
Alex?
Thank you for showing this. When you were talking about semantics, and I was thinking about the non-manifold relationships of inside and outside, I noticed that the manifolds or the worlds broke down when you were talking about the inside of the building. But is there blurring manifolds of worlds outside the building? So I guess in particular, when it comes to using Topologic to integrate a building into its site. So it relates to the landscape and to maybe the sidewalk or a bus stop or
that is definitely a bit of a limitation in that everything that you need to reflect on needs to be represented, and sooner or later you have to put boundaries around your project in order to manage the size of it. So but the good thing about Topologic is that, let's say you're dealing with a central courtyard building or house. The central courtyard should not be unmodeled, should not be left as a vacuum, should not be left as not modeled. It should actually be modeled as a cell, but then assigned, that's where semantics come in, assigned a courtyard or material being air even, if you want, whatever it is, or a void, so that everything is actually made into a cell, and these cells are connected to each other. But we don't make a assumption what this cell is. We don't make an assumption that it is solid or made with liquid or gas or air or void or anything you want. So you use semantics to do that. But you're right in the sense, if you start going out into the environment, I would probably go into landscape software or GIS software, something else that maybe Topologic can connect to.
I see.
So you could have outdoor rooms perhaps that were close, that could be cells in your system if you wanted
Exactly. So they don't have to be solid, but you do have to represent them.
Yeah.
I see.
Great.
Well,
Okay.
thank you very much.
Yeah, that's
Thanks.
great. We have 2 questions in the chat. I don't know if you can see them. So
Not right. Okay.
Just a second.
Yeah.
Okay,
Yeah.
so Patrick, would you like to ask the question? It's similar.
It's been answered in the by one of the earlier questions, I think.
Okay, great. And then Ryan, you had another question? This whole thing about the lightweight and the BIM, would you like to add your comment or talk to Wassim about this? Ryan Schultz? So
He's
he
muted.
basically
I hear
says,
you.
Sorry,
Go
I
ahead,
was
Ryan.
unmuting that. I was just asking a comment when you were talking about eventually breaking that lightweight model with the fully fleshed out BIM model. I would see, obviously can't happen now, but in the future, it would be nice to always maintain that connection between the lightweight model and the BIM model.
Yeah.
You really never break it, but more of a comment.
No, absolutely. And we that's our intention as well. If it is the driver model, you would always have to go back to the topologic model, to the conceptual model, and then rerun your rules in order to regenerate the BIM model. But we don't have a two-way connection as you would imagine it. That would have been, that would be really fantastic. We should move in that direction. Should I read this question from Lewis? Is there a subset of Topologic for mobility? I see great potential to populate urban design proposals, the semantic scheme proposed. Could you, Lewis? Could you just say it in a different way? Could you just explain it to me? I don't want to answer something I'm not fully understanding. Maybe if you could turn on your mic and just ask it.
Yes. Hello. It's a pleasure to be here, Professor Wassim. I was wondering, particularly mobility has a very strict rules of relationship between elements in mobility, different set of transport media. So I was wondering if you were considering for next step for topology, for the Topologic app to incorporate this different set of mobilities rules within buildings.
Right, right. We as a research team, obviously the research team is now me because the project has finished obviously in 2019. So we are continuing, obviously we have open sourced it and we are making it available, but we are concerned with offering Topologic as a foundational tool. We cannot build on top of it domain specific tools. We don't have the capacity to doing that. But we are more than happy to talk to teams who are interested in that and help them get their domain-specific tool built on top of Topologic. So if you have a use case and you want to use Topologic for it, just come and talk to us. But we cannot, because we cannot do urban and do mobility and do BIM and do energy analysis and structural analysis. I know there are people who are interested in using it for structural analysis because of the lines and the vertices. But we don't have the capacity to do that. But we're happy to help you get up to that level.
That's great.
I'm not sure.
I was curious if you could talk a little bit more about the TestFit IO connection. You kind of rushed through that, and it's a very promising software that iterates many, many variations. So it seems ideal for connecting with you.
Yes, indeed. And TestFit and the company and us really have a fantastic collegial relationship. We really appreciate their work and they appreciate our work. So basically, I happen to kind of stumble on TestFit. Take a look at their website, testfit.io. And what they are doing is they are building, again, these very, very simple cellular models, but very quick iterations to find out whether a building fits on its site. You can do all sorts of parametric variation on it to find out, the economic feasibility, setbacks, everything. So, but obviously they create pre-architecture. They don't pretend ever to say this is a piece of architecture. It's basically just spaces. So, I took a look at their models and I thought, oh, that really looks like a topologic model. And if I brought it into Topologic, I can analyze it. I can build a cell complex out of it. I can build a dual graph out of it. So we took all of these things. So we wrote processes that read the files from TestFit, could build a topologic model, and then we start analyzing it. And once we had that, it was Pandora's box. Basically, you can do anything you want. So basically, you can say, give me all the outside faces, all the inside faces. You can analyze the building in different ways. And then, because we know this is an interior face and exterior face, we were able to convert it into Revit models in a very intelligent way. So we can combine all the exterior faces into one long face, and and we did intelligent conversion into Revit models. And now we want to convert it into IFC models because that's our open source philosophy. So that's the next step for us.
That's great. It's very exciting to see this development. So it looks like you have to go backwards to go forwards. Is that the answer? That you really have to go to the core and get the essence? I love your description, the anatomy of a building. So it's a very, very strong idea that you could get to the essence of a building and then be able to manipulate it in so many different ways. So it looks very powerful.
Thank you. Yes.
Okay. So if there are no more questions, I think I'm going to finish the session now. Those people who want to hang on and ask questions, you're welcome to do it. I'm going to stop the recording now. Okay. And then we can chit chat. Thank you so much. Everybody give virtual applause. Let's find that reaction button. Thank you very much. We're clapping here. Okay. So
thank you for having me. Really enjoyed it. Thanks.